So, hello again everyone. Now to talk about something quite different from other oximetry applications. I'm going to be talking about a new concept we've been working on here in Glasgow, which is achieving dye-free retinal angiography using multispectral imaging and a perturbation in blood oxygen saturation. And we've given this technique slightly over the top acronym of ORCA. So just to give you a little bit of an outline, I'm going to talk a little bit about fluorescence angiography and motivation for why doing dye-free retinal angiography would be desirable. And then I'm going to talk about how we achieve this and how we tested it and our results, and of course discussion, future outcomes, conclusion, all that jazz. So fluorescence angiography, now I know there's a lot of people here probably incredibly familiar with fluorescence angiography. It's a workhorse tool for studying the retinal circulation, and it involves intravenous injection of fluorescent dye into a subject's vein, obviously, and an ophthalmologist can look at this fluorescent dye circulate around the retina, first through arteries, then go into the smaller vessels, flush through the capillaries, and then go into veins. And you can see here in this image, for example, the arteries, this is about, the arteries are completely filled, like this artery here. Small vessels are filled, capillaries are filled, and veins are mostly at this point unfilled, but you see a little bit of filling from laminar flow of blood in retinal branching veins. Now, fluorescence angiography is a very powerful tool for studying the circulation, but it has a couple of cons, as I mentioned. Intravenous injection, which requires a specialist, and the dye used is mildly toxic, so there is a risk of nausea, quite strong nausea, and a risk of skin irritation. And speaking to Andy McNaught, who's not here today but was here yesterday, he also mentions that this presents a risk that needs to be considered when addressing a patient's needs if they have complications with other internal organs such as the kidneys. Then you really need to consider the risk of doing a fluorescence angiography, the risk-benefit analysis. The other thing is that the fluorescent remains in the circulation for quite some time before being filtered out by the kidneys. And I haven't underwent a fluorescence angiography, but I've been reliably informed that it's quite an unpleasant thing to go through. If you could avoid it, you'd rather not. But it does give very nice results. So here's an animated GIF showing a fluorescence angiography in process. Here's the arteries filling with fluorescein, and then you see the small vessels starting to fill. Here's the macula here. And then you see the veins starting to fill. For example, this vein filling with fluorescein and also remaining quite dark. And we see as we get towards the later phase of the angiography, you can see many small vessels. And this is a video I just got from YouTube, so here's the source. But it really shows the circulation in very nice detail. So we asked the question, can we use multispectral imaging to provide similar information to fluorescence angiography without the need for injecting this dye? And the answer is yes, we can replicate quite a few features of vessel filling and laminar flow, and I'm going to explain how we do it. So the concept, of course, this is the Oximetry Workshop, so it's based on the endogenous contrast of hemoglobin. So if we look at hemoglobin at a wavelength such as 577 nanometers, blood vessels at 577 nanometers, arteries and veins both appear dark, so veins labeled with the blue arrow, arteries red, and you see these are both dark. They look very similar, absorb similar amounts of light. Well, if we look at an oxygen-sensitive wavelength with lots of contrast between oxygenated and deoxygenated blood, such as a 600 nanometer waveband, I should say this isn't purely 600 nanometers, there's some longer wavelengths in this particular waveband, so arteries are very transparent here. And you can see the big difference in absorption between arteries and veins, and this is, of course, due to blood oxygen saturation and the difference in oxygen content that this makes. So the idea is to use this difference in optical absorption, but we need to perturb it somehow to change it and watch that oxygen perturbation flow through these vessels. So to do that, we've got subjects to inhale a hypoxic air mixture of 5% oxygen, 95% nitrogen, for a very short time, well, 15 seconds. A single deep breath, a deep breath out first, then a deep breath of this hypoxic air mixture, inhaled and held for 15 seconds before breathing normal room air again. And what this does is it produces something like, not quite a step change, but close to a step change in partial pressure of oxygen in the lungs. So rather than the partial pressure of oxygen in alveolar capillaries, rather than being close to 100 millimeters of mercury as it would normally be, it's somewhere between 40 millimeters of mercury, which is venous partial pressure, and 100 millimeters of mercury, somewhere in between. But it decreases the partial pressure in oxygen in the lungs, which of course decreases arterial blood oxygen saturation, and this blood circulates around the body, reaching the retina. We can track this deoxygenated blood circulating through the retina by using multispectral imaging and using the oxygen sensitive and oxygen insensitive wave bands. And then we do some computer processing once we've got this multispectral video to look at the changes. So the computer processing that we do is we've got this multispectral retinal video sequence, so we create a multispectral image stack, then we stabilize the video to eliminate the motion. Then we calculate a pixel by pixel intensity ratio of the 600 nanometer image divided by the 577 nanometer image. And this is where the name ORCA comes from. It's Oximetric ratio Contast Angiography. But this intensity ratio is sensitive to oxygen saturation, amongst other things, but it's the same principle as the red eye measurement that Derek mentioned earlier. And then to reveal the small changes in optical absorption we see, we perform image subtraction, which is basically using computers to spot the difference. So our experiment we carried out, we imaged 11 healthy human subjects, taking multispectral retinal video using IRIS, and once again, IRIS is a very nice piece of equipment to use because we get 8-band multispectral imaging, and we imaged at a rate of 3 frames per second. So we needed 300 milliseconds to give us a sufficient signal through, but we wanted to avoid as many blurred frames as possible, so we wanted to image as fast as possible. We found that 3 frames per second was a good compromise. So these subjects inhaled this hypoxic air mixture, and this produced a decrease in arterial blood oxygen saturation as measured by a fingertip pulse oximeter of between 5 to 15% in subjects, and that lasted for somewhere between 30 to 60 seconds, depending on how fast they inhaled and things like that. The magnitude of the decrease in arterial blood oxygen saturation also depends on how well subjects exhaled and then inhaled the mixture, because they're sitting in this crouched position, so their lung capacity is decreased and they're folded over a little bit. So what we'd see in the intensity ratio, if you looked at the intensity ratio of an entire image, this is a simplified representation. What you'd see is at the start, at some normoxia baseline, and then subjects would inhale the hypoxic air mixture, and we'd expect to see a decrease in the intensity ratio of the entire eye, reaching a minimum point corresponding to the maximum of this transient hypoxia, and then we'd expect them to return to normoxia. And the key thing that we need for this dye-free angiography to work is this change in intensity ratio. So it could either be from here to here or here to here, and we use this point from the middle. It's from point 2 to point 3, because that allows us to visualize this change for a long time afterwards. And this is some data from real subjects. The blue line is, sorry, I've got this label the wrong way around. The blue line is the intensity ratio of the eye. The green line is fingertip pulse oximeter data. So we see the decrease in intensity ratio in the eye first before we see it in the fingertip pulse oximeter, as one would expect. And the shapes, although this can be affected by things like motion, the shapes are somewhat similar for both of these. This one's more narrow than this particular deoxygenation wave over here. And really, the main point is this is the sort of results you get. So here, actually, I'm going to dim the light to let you see better. That's probably as dim as they go. So what you see is arteries filling first as this deoxygenated blood goes through. Actually, this is reoxygenated blood returning to the retina. So it's going from deoxygenated to oxygenated. But you see the arteries filling first, and then, so this artery here, this, you see some smaller vessels starting to fill up. This vein here remains dark with a branching vein coming in from the side, partially filling. There's a branching vein here as well at the top, which is partially filled. And this is pretty nice. I know it's a little bit hard to see. This is on the projector screens, but this gives us something that looks quite a lot like a conventional fluorescence angiography. And to look at one of the key traits of, well, is this a real thing that we're seeing? Well, we wanted to look at the arteries and veins and choroidal sections and see how they filled. So these red vessels are arteries, and we see that the arteries, here's a time along the bottom and just how bright they appear. The arteries begin to fill first and fill brightest, and then the choroid and the veins begin filling roughly about the same time it appears, but the veins lag behind the arteries as one would expect, and the choroid also lags behind the arteries as you'd expect. And I just want to emphasize that although there are other techniques for measuring flow rate of blood in the retina, such as Doppler OCT, these other techniques measure velocity of the erythrocytes, but they don't measure a contrast agent as it flows through different vessels. So other than fluorescence angiography, I think this is the only technique that shows this sequential vessel filling, at least that I know of. Please let me know if I'm wrong. But also we can look at laminar flow. So in this subject's eye, there's two branching veins. So this is a relatively small field of view. I should mention that our field of view in this particular data set was also reduced because there was corneal glare around the edges of the image, so we had to crop to a smaller image region. But what we can see is laminar flow here from these branching veins, and we see this persisting for quite a while. And now the laminar flow here that we can see, well, it's due to diverse oxygen saturations flowing in veins. So if you've got two branching veins, two veins coming in, joining to make a larger vein. One vein maybe has a shorter, the blood takes less time to circulate than blood that maybe takes another path, and these will have different oxygenations, and these flow in a laminar flow fashion, which was one of the things discussed at the Oximetry Workshop 2 years ago. I wasn't there, but we got the consequences, they got the debrief in Glasgow, and this was something that was discussed there. And this laminar flow, I think, is interesting for retinal oximetry because maybe it can help us improve our analysis somewhat. So if you know that there's more than one oxygenation flowing in a vein, well, normally we just assume that there's a single oxygenation. So if we have some weird line profile like this, normally if we're doing some vessel fitting, we would just fit straight through it, fit a Gaussian or something to it like that, ignore something like this. But really, if we know for definite that there's multiple oxygenations here, then maybe we can use this information and fit an alternative fit, and then try and estimate the oxygenation for each bit of these of this branching vein. And I think this might be something that's correlated to vein size. You could expect that larger branching veins may have multiple oxygen saturations flowing in them. And if you're doing like vessel size dependent calibrations, as some people have done in the past, maybe this could affect it. So it's just something to bear in mind. So I want to compare a bit about advantages and disadvantages of ORCA and dye-free angiography versus fluorescence angiography. So ORCA, as I said, is non-invasive. We think it's pretty low ethical risk. We have ethics approval, obviously, for doing it here at Glasgow. Subjects experience almost no feeling of lightheadedness at all. We did this to, we had 11 subjects, maybe 2 or 3 reported feeling lightheaded for a very short amount of time, 2, 3, 5 seconds, something like that. But it was nothing compared to the lightheadedness would maybe, well, some people would feel with more sustained acute mild hypoxia. So this seems quite, it seems to be low risk, but of course you haven't proved that clinically or anything right yet, so asterisk there. Now it's something, if you're looking at vessel filling, you could do repeat measurements of this very quickly. So you could do a different measurement of this every 2 minutes, say. But with fluorescence angiography, if for some reason the subject isn't ready when the vessels are filling, well, you're sort of stuffed because you can only do that about once a day. It takes a long time for that fluorescence to be removed from the circulation. Of course, this oximetric ratio contrast angiography requires computer processing, which fluorescence angiography doesn't necessarily require. And the thing is that we don't think ORCA would highlight vessel leakage, which is a big strength of fluorescence angiography, is looking at microhemorrhages and seeing blood plasma leak out. I appear to be missing the slide, but you could use optical coherence tomography. So there's retinal oximetry done with optical coherence tomography, although there's time resolution, technical limitations there. Maybe the studies I've seen maybe take about 25 seconds to get a 3D data set. Also, magnetic resonance imaging is sensitive to changes in blood oxygen saturation. So you could technically conceive of doing this dye-free angiography with MRI, but of course there's the technical limitations of the long times required for data set acquisition in MRI. But where might we go with this dye-free angiography process? Well, I think there's things that we can do to our existing imaging system in Glasgow to improve it. So it's a very bright illumination light at the moment, so we could probably change our illumination to increase subject comfort, reduce eye motion a bit. We could increase our field of view and pixel usage. Currently we're imaging 8 wavebands, only using 2. So we're throwing away 2/3 of our detector usage, but we could get more pixels and improve the image quality there. We could also do robust vessel fitting. So as I said, we're looking at this sort of crude use of ratios, and but actually in retinal vessels you could calculate optical density ratio, and that will be quite robust, but of course it's going to require a lot of computation time, and it's not applicable to the choroid. Maybe you could do choroid as intensity ratio, retinal vessels as more robust fitting, and of course you could port it to other imaging modalities. So things that you could apply this to, I think you'd really want to compare this to fluorescence angiography in the same subjects. So other flow imaging techniques compared to fluorescence angiography, so it would make sense to do that. And I think the real strength would be studies of vessel filling, things like vessel occlusions and myopia and glaucoma. I've seen publications and studies of vessel filling in myopia and glaucoma, and I would welcome suggestions as to what this could potentially be useful for. And just like to wrap up there, because there's that other one, that slide I'm missing. So just want to say, we've achieved non-invasive dye-free angiography of the retina. We use this multispectral imaging and a high hypoxic mixture to perturb the blood oxygen saturation. And we observe features like laminar flow, sequential vessel filling, that are features that you see in fluorescence angiography, but we probably not going to see vessel leakage. And I think that this laminar flow, these observations, which are laminar flow of different oxygenations in a vein, could be useful for improving vessel fits for oximetry analysis. And I'd just like to acknowledge all the collaborators in this. So we've got Christian Dellis, who's a cardiovascular specialist here at Glasgow, Andy McNaught and Nigel Benjamin at the University of Plymouth and the University of Exeter, who started doing some of these experiments way back, and obviously Andy and Javier. And so thanks very much for listening. We have to take any questions.